So soil is very significant because it covers much of Earth's surface and is a medium for plant growth, which obviously we need as our primary producers. It's a filter for water, as water moves from the atmosphere into rivers and streams and groundwater. Soil helps filter that water. It's a habitat for living organisms. It helps filter pollutants. Soil is a mix of geological and organic compounds. It takes hundreds of thousands of years for soil to form. So even though we consider it to be renewable, it really isn't in our lifetime. It results from the physical and chemical weathering processes, this breakdown of rocks that we just spoke about, and the deposit of organic matter from organisms and their waste. The parent material is what the soil is made of, that underlying rock material. The type of rock will determine the type of soil. So quartz sand, made up of mostly silicon dioxide, will give rise to a soil that is nutrient poor, like things along the coast. Something like calcium carbonate will have an abundant supply of calcium and support some high agricultural productivity. Climate also influences soil. Very cold, soil doesn't form well because the decomposition of organic matter and water movement are very slow or frozen, nearly frozen soils. Humid tropic soil formation is accelerated because that rock weathers very quickly, but nutrients leach quickly. So climate also influences the type of vegetation that develops, and that will also decay. Topography factors into this. Steep slopes are constantly subjected to erosion. Soils forming in valleys may continue to accumulate material from higher elevations and become deep. Organisms influence soil formation. Plants remove nutrients. Animals tend to burrow, things like earthworms and gophers and voles. And then time. The amount of time a soil has spent developing a soil. Its age, they develop a variety of characteristics. And that's a lot of what I was talking about here. So soil results from physical and chemical weathering, that parent material, climate, topography, organisms, and time are all the factors that are important in this formation of soil. If we look at this diagram, we can see immature soil where there's a lot of parent rock, and the parent rock is pretty high up to the surface. As we go through time, we have younger soil, so we have more organic material accumulating as plants and other organisms die. And you can see that this parent material is a little bit more broken up. And then as we have mature soil, greater amounts of organic material are present in mature soil. It supports larger plants that are able to grow. And these roots are able to permeate much better, which is part of the reason they're able to support bigger things. Soil horizons. You need to know this as part of your APES course. There's these distinct layers that we looked at in several different forms. If we start at the bottom, if we start at this sea horizon, this is your parent rock. This is your weathered parent material. And sort of we refer to as the bedrock. We move up and we have this B horizon. This is the accumulation of metals and nutrients. It's a subsoil. It's primarily mineral material, very little organic matter. It's broken up parts of our parent material. In between, sometimes between from A and B is an E layer. I'll discuss that in a second, so we'll work our way down now. This O horizon, this is the organic matter in various stages of decomposition. So these are your leaves, needles, animal bodies. It's a dark brown color. It's the things that are along the top that are on their way to decomposing. That A horizon is our topsoil. That's sort of the magic small little area here that's so responsible for plant life. It's overlaying organic material mixed with the underlying mineral material. And mixing can occur naturally by human agricultural practices or by organisms that burrow and weathering and other rain and things like that. The B horizon, like we said, was this broken up parent material. So sometimes in between A and B, there is an E layer, which is eluviation. It's not shown in this diagram, but that's typically where it occurs. It's a zone of leaching. It can form under that A horizon. It's always above the B horizon. And it's where iron and aluminum and dissolved organic acids from the overlaying horizons are transported through and removed from the E horizon and deposited in the B horizon. So there's this sort of this zone of low minerals in here. It doesn't occur in all soils. And if it is going to occur, it's going to be between the A and the B. So it's OABC, but sometimes it's OAEBC for that alluviation layer. Texture, this is the percentages of sand, silt, and clay in the soil. So we learned how to read that diagram so that we can find what type of soil we have. Loam is the word for the type of soil that we like the best. It's the best combination, the best ratio of sand and silt and clay. We know that we need all three types of these particles in order to have good quality soil. We need enough sand to allow water to move through. Clay doesn't allow water to move through, but then clay also holds on to nutrients. Silt is sort of that in-between area. That's good just for both ends of it. So clay is really impermeable. Roots can't go through it. Water can't go through it. But it's going to hold on to those nutrients. Sand is good because it's porous. It's going to allow the water to go through. It's going to allow the roots to be able to burrow. But we want sort of that sweet spot. We don't want, it's like Goldilocks. We don't want too much. We don't want too little. We want it just right. Permeability is how quickly the soil drains, which depends on its texture. The best agricultural soil is a mix of all three of those, like I said, the loam. Okay, so if we were to put water over sand, it would take an hour for a certain quantity of water to go through. If it was silt, it would take 100 days. And if it was clay, it would take 100 years. So it's really showing you that permeability. Chemical properties of soil, that CEC, cation exchange capacity, the ability of soil to absorb and release cations, positively charged mineral ions. Clay particles attract positively charged mineral ions, soils with high CECs. Soil bases, things like calcium, magnesium, potassium, and sodium, promotes plant growth. Soil acids such as aluminum and hydrogen are detrimental to plant nutrition. Base saturation is the proportion of soil bases to soil acids. Biological properties of soil. Many organisms are found in the soil. The three main groups of organisms are equal to 80 to 90% of the biological activity in the soil. So things like detrivores, things like soil-fixing bacteria, that ammonia-fixing bacteria that we learned about that was so important to the nitrogen cycle. Things like rodents and earthworms, snails, and slugs. We have our things that are going to break down organisms as they die and decompose. Our detrivores, we have our organisms that are going to help fix that nitrogen into place so that our plants have access to it, that nitrifying bacteria, denitrifying bacteria, all of those that were so important to the nitrogen cycle. And then just our organisms that just live there that are important to the nitrogen, that are important to soil. Soil degradation is the loss of some or all of the ability of soils to support plant growth. Occurs in overuse of land for agriculture, forestry, and other human activities. Soil erosion, if we don't have enough roots or things in place to hold that soil in place, that soil will be washed into waterways and taken away from areas where it's usable. Compaction of soil by machines, humans, and livestock, mushing that soil down so that it's not a layer that can support growth and life as well. And then extensive agriculture use and irrigation. And then our last part is mining. And we've had some experience with mining. Elemental composition of the Earth's crust. We have finite quantities of rocks, minerals, and fossil fuels. We know how much we have of that because we're not getting anything new unless we have some sort of meteor hit, which isn't going to bring a large amount of quantity of things in. Crustal abundance, average concentration of an element in the Earth's crust. And we can see the chart that tells us that composition. And obtaining mineral resources, so things such as ores or metals. Reserves are the known quantity of a resource that can be economically recovered. Some reserves in the U.S. have already been depleted. Your textbook is 5 or 6 years old already, and so some of these U.S. reserves we've already gone past. So we can see the global reserves, but then we can also see the United States reserves for some of these things. So iron, there's only 40 years left for the U.S. Aluminum, we should have technically used up based on this chart and the data, because it's 2007 is this data. Copper, it's a big 40 years, lead 40 years, zinc 25, and this is at the rate that we are using it to. So you have to take that into account. Maybe we are recycling more aluminum, so we don't have to mine as much aluminum, and we have better practices. Types of mining. So this diagram shows us different types of mining. Surface mining, mineral and energy resources are extracted near Earth's surface by removing soil, subsoil, and overlaying rock. It's more common because it's less expensive. There's open pit, which is here, or there's strip mining, which is shown over here. Open pit, you remove the overburden. You dig a big deep hole in the ground and remove what you want. Strip mining, you remove the overburden, you dig trenches, and the overlying soil and rock is dumped into the previous trench. So you dig a trench and then you dump the next one into the next trench. Subsurface mining is looking here, and that's what we sort of think of when we think of our coal mines. Mineral and energy resources are extracted from deep and underground deposits. There's two kinds. There's a shaft mine or a slope mine. Shaft mine uses arrows, allows entrance and exit from the mine, uses an elevator or pulley system. A slope mine is an entrance dug on a slope down the ground, uses like a rail car system. Both of them we sort of think about with coal. Placer mining is what we think of the gold rush days, where you just went and sort of picked up, sediment from a stream and washed through and looked for gold. The original gold rush people were placer miners. And then mountaintop removal is sort of the same as open pit. Open pit is you're digging a big hole in the ground. Mountaintop is you're essentially blowing off the top of a mountain to get at what is below the surface of that mountain. So to sort of recap, surface mining, mineral and energy resources are extracted near the top. It's more common because it's less expensive. There's open pit and strip mining, and then that subsurface mining with the shaft mine and the slope mine. What are the effects on the environment between surface mining and subsurface mining? Effects on the air for surface mining, there's significant dust. Subsurface mining has minimal dust, but because we need fossil fuels to power mining equipment, there's significant emissions. Effects on water. Surface mining contaminates water that percolates through the tailings. That's that overburden or the stuff that's extra that's left over. Subsurface mining has acid mine drainage, as well as contamination of water that percolates through those tailings or that overburden. That acid mine drainage is really hard to remediate. Effects on soil. Most soil is removed from the site, can be replaced if there's reclamation. Subsurface mining, you disturb much less of the soil because you're digging in, sort of tunneling below. Surface mining effects on biodiversity, you are destroying and altering the habitat over the surface of the area that's mined. Subsurface mining will have less immediate impact, but road construction to mines will fragment the habitat. And then the effects on humans. For surface mining, there's minimal in the mining process, but air quality and water quality can be adversely affected near the mining operation. Subsurface mining has the occupational hazards in the mine. Death or chronic respiratory disease, black lung from breathing in that, and then there's just mine collapse, where people become either killed or trapped in subsurface mining. Mountaintop removal is removing this entire top of a mountain. There's a picture that's used explosives. Damage to streams and nearby groundwater cannot be rectified by the reclamation process because it's such a violent way to mine. And then placer mining, looking for metals and stones in river sediments, much less common today. There are some mining laws. The effectiveness of it has varied. The mining law of 1872, the goal was to regulate the mining of silver, copper, and gold ore, as well as fuels, including natural gas and oil on federal lands. And then the Surface Mining Control and Reclamation Act of 1977 regulates surface mining of coal and the surface effects of subsurface coal mining. So trying to put in some laws to enforce that reclamation, but it's all, you're your laws are only as good as they